Welcome, everyone. Today we have a great guest speaker, Josh McGarrick. So today we're going to be talking about precision monitoring with Spectral Evolution and Orbital Sidekick, utilizing space-based hyperspectral imagery and ground-based spectrometry. So we have a short project that we did partnering with Orbital Sidekick. And so first, I'll start off just by introducing us, and then Josh will take it away with more of the technical expertise and Orbital Sidekick side of things. So Spectral Evolution is the leading manufacturer of ground-based or field-based hyperspectral spectroradiometers and spectrometers. We cover the UV, Vis, and IR range from 350 to 2500 nanometers, and we've been established since 2004 and located in Haverhill, Massachusetts. And so since we're talking a lot about remote sensing, I'm going to harp on that a little bit more. But our primary applications are in hyperspectral applications, remote sensing and vegetation, mining and geology, as well as photonics and calibration transfer. And a lot of these applications are the same for Orbital Sidekick as well. So I'm just going to talk very generally on spectral resolution and why it's good to use a field-based instrument alongside these satellite-based remote sensing instruments. And that's because typically there can be limitations. In this case, it'll be more spatially, but spatially, spectrally, and temporally, there can be limitations, and you can get on a sub-pixel level with a field-based instrument. So most remote sensing surveys are greatly improved by field-based hyperspectral data for validation or ground truthing. UV, Vis, and IR technology allows for vicarious calibration, so you can target with a satellite. Satellites can't come out of the atmosphere to be calibrated, so you can target a known target on the ground and calibrate those satellites based on what you see on the ground. So you could use one of our instruments on the ground and scan something and then scan it with the satellite, and you can make corrections for satellites. So that's a very common way that these instruments are intertwined. And so for this showcase, we collected high resolution scans of urea, blue paints, and other materials so that we can compare to satellites and create high resolution spectral libraries that you can then apply to satellite surveys and start monitoring on a grander scheme. Because there's point spectrometers, you're going to get one point. It can be a few millimeters or it can be a meter, but surveying a whole region, it's important to be able to intermingle these kinds of data sets. So now to introduce Orbital Sidekick, who's going to go into more detail on all those satellite images and their data products, I'm going to introduce Josh McGarrick. He's the Director of Government Programs for Orbital Sidekick, where he generates space-based hyperspectral images, use cases for government customers, performs business development primarily for defense and intelligence, and fulfills other contractual duties. Prior to joining OSK, Mr. McGarrick previously spent nearly 20 years with the National Geospatial Intelligence Agency in Springfield, Virginia, where he similarly led, managed, and performed HSI processing and automation research and development for the government. During his tenure at NGA, he served with the Source Analysis and Research Directorates, supported 5 deployments to Afghanistan, and chaired the Spectral Radiometric Working Group, SWG. He was a recipient of 2 Joint Civilian Service Commendation Medals, a National Intelligence and Meritorious Unit from George Citation, and a Challenge Coin from General David Petraeus. He holds an MS in Geoinformatics and Geospatial Intelligence from George Mason University and a BA in Geography with a focus in GIS and remote sensing from the University of Colorado Boulder, and presently resides in Northern Virginia, USA. So to introduce Orbital Sidekick, and I'm sure Josh will elaborate on this a little bit more, OSK operates the most advanced constellation of hyperspectral satellites, providing a chemical fingerprinting capability that distinguishes it from traditional optical imagery. Their satellite constellation captures the highest resolution hyperspectral imagery in the market with 8-meter GSD and 472 spectral bands from V-near through SWIR. OSK is focused on providing a global persistent monitoring service with space-based hyperspectral data for private and public and defense sectors end users who require rich targeted insights and advanced HSI data at scale. So, like I said, we've worked with Orbital Sidekick a lot, and a lot of our customers work with Orbital Sidekick data products as well. So it was great to have Josh here today, and I'll let him take it away from here.
Okay, thanks, Mac. So
Yep.
I will, yeah, thanks for that great introduction. I'll go ahead and share my screen here if I can figure out how to do that. Okay. All right, so I'm going to just start off with a couple of PowerPoint charts, and then I'm going to take the risk and jump into a live demo. Should there be any issues with the live demo, I can come back to the PowerPoint charts, which I'm going to do later anyway. Yeah, so again, I'm Josh McGarrick, Director of Government Programs here with Orbital Sidekick. Sort of per Mac's introduction, I've been with OSK for just over a year now, and actually it's almost a year and a half at this point, but formerly spent nearly 20 years with NGA in Springfield, Virginia. And right, so now as the Director of Government Programs, I primarily I manage some of the government contracts that we're on. I also can exploit hyperspectral data and search for use cases that are primarily related to defense and intelligence. And that's sort of what I'm going to show you here. So I wear multiple hats being with OSK. So I'm going to hop over into it. So about Orbital Sidekick, sort of following up on a few things that Mac had already brought up. 472 spectral bands. At one point we had 5 satellites on orbit. We actually had Ghost number 2, or G2 actually deorbited about a month ago. So we now have 4 satellites on orbit. That's Ghost 1, 3, 4, and 5 are currently on orbit. We are in the V-near SWIR, the visible near infrared and shortwave infrared portion of the electromagnetic spectrum, covering the 400 and 2500 nanometer portion of the spectrum. In terms of what we can actually do, gas detections, we're primarily focused on methane in the gas perspective. Methane is one of the few gases that actually has absorption features that are in the V-near SWIR portion of the spectrum. There are a few other limited things that we've explored with respect to gases in the V-near SWIR portion of the spectrum, but we do primarily focus on methane. Chemical signature identification, this is really where I think the power and the magic of visible near infrared, shortwave infrared, hyperspectral comes into play. I'm looking for a variety of solids materials specifically on the ground. So they could be chemicals, they could be something like a camouflage, they could be paints, they could be metals, things of this nature, some of what you see listed here. And then of course also solid materials also include minerals, geologic things, geologic features, rocks, and so on. And of course, we can address these sorts of things for oil, mining, gas, energy, and a variety of other customers on the commercial side of our business. Again, I primarily reside on the defense and intelligence side, but we do have a commercial side of our business as well. HSI Constellation. So the company was started in 2016 by Dan Katz, my boss, and Tushar Pravakar, our chief operating officer. We flew sort of as a minimally viable product or an initial demonstration, a V-near only sensor on the International Space Station that was known as HEIST, followed up with a free flyer that was 30-meter GSD, full V-near SWIR in the 30-meter GSD realm, kind of similar to a tanager, to a planet tanager system. It was a free flyer. Unfortunately, only collected one shot before it actually malfunctioned, and that launched in 2021. We followed up that free flyer with the GHOST constellation, or the Global Hyperspectral Observation Satellites, and that started in 2023 with the launch of GHOST satellites 1, 2, and 3. And of course, our GHOST constellation has the 8-meter GSD. and that is currently the highest GSD satellite on orbit that provides the full linear SWIR. So that was Ghost 1 through 3 in 2023, and then followed those up with Ghost 4 and 5 in 2024. We still do have Ghost 6 sitting on the shelf. Ghost 6 is effectively a completed satellite that's sitting on the shelf, and we're hoping to get it launched either later this year or early next year. And it contains effectively the same specifications as Ghost 1 through 3 and 4 and 5 as well. So that's sort of the timeline of the constellation. Looking a little bit more in depth at the specifications, kind of the main thing I'll point out here is, actually I don't even see it listed on here, but I was gonna cover our swath width. So I'll just jump into, well, before I talk about that, I'll say we are in the sun-sync orbit. So all of our satellites are in the sun-sync orbit. So they all have, the ones that are on orbit right now will have afternoon local time of descending node, meaning we're going to cross over and collect our targets primarily in the afternoon time frame per the orbit that our satellites were injected into. Ghost 1 and 2 actually had a morning LTDN, meaning they crossed over in the morning. We've actually found out, as I've looked at a bunch of data, a good number of customers have actually requested data plus or minus 10 or 15 degrees from the equator, and crossing over in the afternoon actually affects that because it gets cloudy down there in the afternoon. So having the morning LTDN could be something that would be a better, potentially a better, something better to look at in the future for future constellations. So that it's not as cloudy around the equator for customers that are collecting data, Philippines, Colombia, Venezuela, places like that. It's cloudy there in the afternoon. This just goes to show traditional systems as we put them. So multispectral systems. Think about 4-banded multispectral systems. So worldview, GeoEye systems like that. Planet, not talking about Tanager, but traditional 4-band multispectral systems can detect. They can detect things that are down there on the ground, and that's what we see on the left-hand side. They can detect and they can see color. They can see the visible near infrared typically. Now, I know some of the multispectral systems are what they call superspectral systems, such as Worldview 3, might go into the SWIR, but you're still limited by the number of bands that you have. Worldview 3 having 16 bands. So on the left-hand side, you can detect things. So if you see white materials on the ground, you can detect that there's something white on the ground. You can detect that there's a tank on the ground or an airplane. But what we try to get into with hyperspectral is the ability to identify. We want to be able to identify what's down on the ground. So be able to identify, if there's a white powder down on the ground, what is it? Is it flour? Is it salt? Is it concrete? That's what hyperspectral can tell you. And that's why we're here to identify what's down on the ground. So that's where you get into what you see on the right. And then you get into characterization. Now that you've identified what's down there, how much of it is down there? If it's a gas like methane, what's the flow rate? How much gas is coming out? If it's a powder, how much powder is down there on the ground? How many square meters? How many cubic feet of the powder is down there on the ground? And then from the insights, what does that then tell you from like an intelligence perspective, or from a why is this stuff down there? Why do we care? So that's what I go to show here, and then I'll hop right into it. I'm actually going to pause on this chart. So this is Merper Pakistan. In this shot, there is a chemical that we're going to go hunt down and look for. And again, this is an Orbital Sidekick image. This is a true color hyperspectral image. This was collected on the 1st of November of last year. So in this shot, you can see that there's stuff down there. I mean, I see roads. You could just say, tell me what you see. You see roads, you see probably ponds, you see buildings, you see clearly agricultural fields, some of which are healthy vegetation, some of which are dead vegetation, but we can't quantify that only by looking at the data. You see possibly villages, houses. What else do I see? I see white stuff, and that's kind of all that I can kind of tell you from this true color image. So for a fast second, I'm going to stop sharing, and I am going to bring up the live demonstration. Okay, so here you have a cube that I've actually loaded into the Envy software. And I'm just going to, well, I'm not going to minimize this. I'm going to leave this here. So these are actually the original 2 data sets right here. We collected them in certain sequences, as we call them. And I've actually mosaicked those together preemptively, these 2 sequences right here. So sequence 4 and sequence 5 of that particular collection, these are collected on the 1st of November, again, of last year at 10:13 Zulu time. And Pakistan, I believe, is 3.5 hours. It's either 3 or 3.5 hours ahead. So you're looking at approximately that would be 1:45-ish, around 2 o'clock local time in Pakistan is what you're looking at here. And I'm actually just going to close these 2 sequences here so they don't confuse me later. So I'm going to go ahead and maximize this data cube, and I'm going to pop open the spectrum. And I'm just going to kind of scroll around in the spectrum for a second. I'm just going to look around. So what you're seeing here is you're seeing a radiant spectrum. So we are looking at this data in radiance. And this is a seminar. So I might try to pop quiz some people in the seminar here. So firstly, we're looking at the radiance here. And what you see here is very simply a Planck curve is what you see here. And I was going to, actually, I'm just going to stop sharing for another quick second. And I'm just going to actually, all I just did was I just ran a quick Google search, and I'm gonna reshare my screen here. I did a quick Google search, and I typed in solar Planck curve. And so what you see here, again, you can see them all here if you just type in Google solar Planck curve, and you can see this is generally speaking what the Planck curve should look like of the sun. If you're looking straight at the sun, reflecting off, this is what the Planck curve looks like. But we're looking down at the Earth, you get various absorption features through the Earth's atmosphere when you're looking down at the Earth. So you're not going to get a straight curve like this when we're looking down through the atmosphere of the Earth. There's going to be various absorptions that are going to come into the Earth, and you actually see some of them here. And that was going to be part of my pop quiz, but I actually partially ruined it. But I'm going to come back and reshare my screen again. I'm going to come back to this radiant spectrum that we're seeing in the orbital sidekick data. And I'll ask people, what do you believe this feature right here is? What's absorbing here in the Earth? And I'll just pause there and see if somebody wants to try to answer that. Somebody raise their hand. And by the way, I don't know if everyone's muted or if people can unmute and talk or what. Tom Korean raised his hand.
Yep. So I can, if you raise your hand, I can open your microphone. So Tom, you're muted right now. So you have to unmute your mic.
That's the 762 nanometer oxygen band right there.
Yes, Tom, that is correct. That is the oxygen band, and there's some other things that are in the data as well that you'll see absorb. So I like always looking at these. These are this is where water absorbs in the atmosphere. So water actually is not in these particular. I call them the 1.4 or 1.4 micrometer or 1400 nanometer and approximately 1900 nanometer areas where water does not transmit in through the atmosphere. So we cannot see through, if you will, those portions of the atmosphere. So I will, I can look at, a lot of data here. I can also, let's see, I believe this is memory 7. So I can display this as a false color image as well. So now you have the vegetation, which turns red because it reflects in the near infrared. Just load that to current. There you go. And I can load different band combinations here as well. So now what I'm going to do, I want to start processing this data now. So what I want to do is I actually want to get rid of all the stuff that's here. I want to get rid of it, and I want to get down to the surface, to what's called surface reflectance. So what I want to do is I want to get rid of as much of this stuff, these things as possible here, and I want to get down to surface reflectance. So what the algorithm that I would run, or that I'm going to run, I actually already have. This is the only one because it takes. I'm not going to run Flash. I clicked on the wrong button. It just bombed on me, of course. So I can yeah, I apologize, folks. That's what happens. So I clicked on the wrong button and Envy crashed on me because Envy doesn't like me on certain days. And I was actually expecting at least something like that to happen to me during this demo, during the course of this demo. So I let's see here. Just get this reloaded here. It's just going to take me a quick second to sort of get back to where I was here in a quick second. But I'm actually pretty quick at this. Okay. Gives me a chance when I at least get a cup of coffee in here. Okay, I've got my mosaic back. Okay, so I am back to the mosaic here. And so what I want to do is I want to apply what we call an atmospheric correction to the data to get rid of these features. I want to get down to surface reflectance. So the algorithm, I've had this pre-run, but since it's bombed on me, we'll have to run it here in real time. So I am going to go ahead and apply the atmospheric correction. The algorithm that I use is QAC, which stands for Quick Atmospheric Correction. And it's an atmospheric correction algorithm that's actually written by the company Spectral Sciences. We've licensed it through the Envy software here. So I'm going to hit OK. And for Orbital Sidekick data, there's a bunch of different sensors that it gives you in here. For Orbital Sidekick data, I've noticed that I actually get pretty good results out of using the generic and unknown sensor. And I'm just going to go ahead and export that to the memory. And again, this takes about 1 minute to process on here, maybe about 1.5 minutes to get. I had this pre-spawned earlier, but at this point, I'm going to have to wait for it to process. So again, it's going to get rid of a bunch of those the features that interfere with that come through the Earth's atmosphere. So we're going to get it down to surface reflectance because I want to see what's down. I want to get the reflectance of the materials that are on the ground. In other words, there's all this stuff between the sensors, which are, oh, by the way, flying at about 500 kilometers above the Earth. So there's all this air and aerosols and dust particles and moisture between the sensor that's looking down to the ground and the surface. So this is what this algorithm's doing, is trying the best that it can to get rid of all that stuff that is between the sensor and the ground. Now, one thing is, some people don't want to look down at the ground. Some people want to look into outer space, or they want to look at the moon, or they want to look at other objects. If you're doing that, it's actually a little bit easier because you don't have to go through the Earth's atmosphere in order to look at that stuff. So if you're a satellite trying to look at the moon, if you're a satellite trying to look out at stars or something like this, you don't have to look through the Earth's atmosphere, so you don't necessarily have to worry about atmospheric correction. There might be some other particulates or matter that you are concerned with, but if you're looking through outer space, you're not looking down at the Earth, so it's a bit easier. So the QAC algorithm here has completed, and now if I load a Z profile here, you actually see that my spectrum has changed quite a bit since we were looking at it before. And I'm actually I get a pretty good result out of this one. So I will load the color infrared, and we'll come over here back to the spectrum. I like just scrolling around. You see, I'm getting a pretty good for those of you experienced, getting a pretty good atmospheric correction on the vegetation here. So that's a good initial sign. Looking at some of the dead vegetation, pretty good signature on the dead vegetation, among other things that are in this cube. We can come up to the water and we look at some of these, and you can see some of these have some interesting things in them. I don't know what's in them, but there's definitely some interesting things going on in these ponds here. And then there's more water over here. And you can see it's probably not just water, there's probably some other stuff that's in the water as well. And what I like doing, I can zoom in as much as I want, all the way to the single pixel level. And literally, when we say we want to spectral fingerprint the entire Earth, for every pixel, literally every pixel that's in here, you can see the spectral signature change. For every one of these pixels, I get 472 spectral bands all the way across the electromagnetic spectrum. And I can go to different stuff, and I can look at different pixels. And every single pixel has a different spectrum coming across here. And you can see that spectrum change with every single one of them. So I now have surface reflectance, or as best possible surface reflectance, for as good as that algorithm can produce. So now what I want to do is I want to start cleaning up the spectra a little bit. I want to clean up the spectrum. So you can see the water, what we call the water regions, the 1.4 and 1.9 regions, Quack zeroed out some of those bands. And you can see some other interference from some of these other bands in here. So the first thing that I like doing personally is I'm actually going to average some of these bands together. So I'm going to do what we call a spectral binning. So I am going to basically take, for every two bands, I'm going to average those two together and create another one. So I'm going to take, for example, if I zoom all the way in here, you can see individual bands. So there's 1, 2, 3, 4, 5, 6, 7, 8. So what I'm going to do is I'm going to take the first two bands, I'm going to average those two together, and I'm going to create a new one. I'm going to take the next two bands, I'm going to average those two together, and I'm going to create a new one. Now, obviously, I'm not going to do that manually. I'm going to use the algorithm that's available in NV up here, and it's under the Tactical Hyperspectral Operational Resource, otherwise known as Thor. There's a tool here, and it's called spectral binning. And I'm going to do that on memory number 2. I'm going to hit OK, bands per bin 2. Some people get actually better results if you go even north of that, 2, 3, 4, 3, 4, 5, etc. I'm going to keep it to 2. I'm going to put that back out to memory. Another sip of my coffee. And I am going to, so this is now complete. I'm going to reload this. And I'm going to look at the Z profile again. And you can see that the spectrum, it now looks a little bit cleaner. The spectral looks a little bit cleaner here. And it's not as what we call noisy. There's not as many inconsistencies in the constant signal. That's the definition of noise. So you don't see those inconsistencies in the constant signal. So the next thing I want to do is I want to get rid of what we call the bad bands. We want to get rid of what we call the bad bands. These atmospheric features, I'm going to call those bad bands, where we get some noise in the focal plane or possibly even a little bit of miscalibration, can be towards the beginning and end of the electromagnetic spectrum. So one way of doing that is we can look at the spectrum just like I'm doing here. I can zoom in and I can say, okay, that's band, let's see, 104. I'm looking in the lower left here. 104, 105, 106. I call these bands bad. That's one way of doing it. Come over here. These are all zeroed out. Quack zero them out. Those are what we call bad bands. We want to get rid of them. Okay. Again, over here, probably, 229, etc. Those we want to get rid of. Another way of doing this, so we can visually depict it, I can run an animation. And I'm just going to make that window a little bit larger. So let's see, I'll multiply this by 262 by 800. And I'm just going to animate the bands. And you can see, here's the bands. Here's what it looks like. Just animating them, single band, pangrammatic. This is just, I'm looking at one pangrammatic band. I can display any one of these bands over here as a single channel if I wanted to. And that's what I'm doing here. So coming across the spectrum, you can see certain bands just aren't good. They're literally bad. You can't see through those portions of the spectrum. So I'm going to get to the really bad portions of the spectrum over here. So here you see literally when I say the atmosphere doesn't transmit, That's what it looks like when it doesn't transmit at those features. And when it goes completely black, that's where Quack actually has just said, I can't even see through there. I'm just zeroing those bands out. And so you can see it's just fuzz. That's why we want to get rid of those portions of the spectrum. That was the 1.4 micrometer absorption feature. This is going to be the 1.9 absorption feature over here. And you can see it's just, these are zeroed out. And then these are not zeroed out, but we still want to get rid of them. They're fuzzy because that's the water that doesn't want to transmit there. And then we get towards where the focal plane doesn't it's not sensitive to this portion of the spectrum. So we want to get rid of those as well. So because I've looked at so much OSK data, I actually have those memorized. I already know which ones I need to get rid of. So I'm going to come up to resize data, memory 3, spectral subset. And I'm going to come to the beginning. I'm going to get rid of the first 8. That's sort of the blue portion of the spectrum. And then I'm going to get rid of, this is another water absorption feature here, 61 to 65. And then 81 to 85, there's water that absorbs there as well. And then 104, let's see. By the way, all this can be automated, but I like doing it manually to show you guys how it's actually done. If we're doing it manually, 156 to 176, and then 180 to 182. And then that end portion of the spectrum, 229 to 236. And then I'm going to be left with 168 bands. And I'll hit OK. I'm going to export this to the memory, hit OK. And then memory 4 is now created. And we now look at the spectrum and we get really nice kind of smooth looking spectrum here with all those bad bands removed. It's continuous for the most part. And you can see the vegetation. We can come back and look at these ponds again. I don't know what's, these ponds boggle me. There's definitely something growing in them. If I display this band here, you can see that some of them turn red. There's some, I probably wouldn't want to go swimming in here. There's something growing in here, in this one, and something growing over here too. And you can see, some near infrared absorption there. Anything growing in here? No, he might be pretty much water. This one down here, this is, I don't know if this is like over irrigation. I don't know if this is a pond down here, but yeah, probably wouldn't want to go swimming in those there. Nevertheless, you can see the spectral signature here is very smooth going across, which is what we're looking for. And some people might have noticed that there's, if I reload the true color, and let's see if I can get this, the scroll window here maximized. Sometimes envy, there we go. Try to maximize the scroll window. If you look here, there's a little bit of cross-track equalization issues going on here from the left to the right or the vertical. And you can see some striping in the data as well. That's pretty standard for hyperspectral systems. That usually gets corrected. When Orbital Sidekick delivers data, we like delivering data as the calibrated radiance data. We like having our end users or customers correct that for themselves because different people like using different algorithms to correct that sort of thing. Some people do complain about it. And we can run some of our own corrections as well, but I like having the customers correct that themselves. So I like just using, there's actually I like using the one in Thor as well called destriping. And this actually works pretty well. So I'm going to go ahead and destripe memory number 4, and I'm going to get rid of the vertical lines or just correct for the vertical lines on memory 4. And we'll see if we turn out a better result here. I think we do. So if I load the true color here, and if we just compare memory 4 and memory 5, you can see here that actually it does a pretty good job at correcting for it. So if I link these two displays, you can see there it does a pretty good job at correcting for that. So here was the original, and now you see you have like a pretty well corrected data cube over here for some of those issues that were going on. I mean, it could probably be better. You could probably get some scientists in a room and people could start competing over detection scores, and mine's 0.01 better than yours and things like that once you actually run the detection. But what I call this this is the final cube ready for exploitation. In my opinion, we're ready to rock and roll here, and we're ready to actually start looking for some spectral signatures in here. Oh, down here, so that's I'm on top of something down here. That's a pretty good that's right on top of 2.32. That's probably calcite down here over here. I know the USGS people like looking at those stuff, that the rocks down there. But what I'm going to do is I'm just going to stop sharing for a second, and I'm going to load in some spectral signatures. And these spectral signatures, Mac actually provided. That's why we're online today, because collaboration between Spectral Evolution and Orbital Sidekick. So I am going to load a spectral library, and I'm gonna reshare here. So I have now loaded in a spectral library up here, and I'm going to get rid of these two. I've loaded the spectral library. So Mac was gracious enough to provide me with, and Mac, I'm going to quiz you, which spectral evolution spectrometer did you collect these with? Please refresh my memory.
Second. Yeah, so we used a NatraSpec Ultra, which is our highest resolution spectrometer. But we are, for this kind of application, most commonly we'll see a NatraSpec Plus or the NatraSpec, which all are competent uses of our instruments. So these are high resolution, hyperspectral. Our NatraSpec Ultra is the highest resolution spectroradiometer on the market currently. So oftentimes people build their spectral libraries using our instruments. They'll take samples out in the field, build that spectral library, and then they can apply that spectra, because we don't have to deal with the atmospheric correction at all, because we're on the ground under the atmosphere. So that's the benefit that we have with that ground-based unit. So.
And Mac, do you have, it looks like you have a spectrometer sitting there next to you. Do you have a probe there, or can you just show the bare fiber to people?
Yeah. So, so we have, one moment.
So basically, instead of a space-based platform, what Spectral Evolution has is a point spectrometer, and what they can do is put the probe or the bare fiber right on top of the material to be measured, and then that's how we get the spectral signatures for ground truth. And so if you look at Mac up here in the video, you can see that is what collects the spectrum of the material. So you just put that right on top of whatever it is you're trying to measure. Obviously, once the spectrometer is on, calibrated and ready to rock and roll, and then you collect the spectrum.
Yeah, so I have the bare fiber here. So at the end of the bare fiber, we have a 25-degree cone field of view. So we have a whole host of different accessories that hold the fiber in place so that you can take a standoff measurement, and you'll be able to see that in some of our other webinars where we showcase the actual field of view measurement, but this is what it looks like. So this is a camera and a distance calculator, so you can calculate what exactly your spot size is. But we also have these contact probes, which supply their own light inside them. So you just connect to these, and this one will give you a 10 millimeter spot size, or this will give you a 3 millimeter spot size, and it has a high energy tungsten halogen light source in here, so you get ample signal across the whole spectrum. So here you can see it's a flashlight internally, and then your fiber is right in there. So you'd go into direct contact with your rock sample or whatever material you're trying to look for in those satellite images, and you'll be able to get really high resolution library spectra to compare to. So that's the order of operations.
Yeah, thanks, Mac. So we so that's exactly what we did. So Mac collected a couple spectrum and was gracious enough to give us those spectrum. So the spectrum that I have loaded here are calcium hydroxide, urea, and blue acrylic paint. And you can see that every one of these spectrum looks a little bit different. And like Max said, if you're directly measuring the material on the ground, you don't have to deal with all the atmosphere between you and the material you're measuring that's on the ground. So you get direct measurements of it. You're not 500 kilometers away, 450 kilometers away, like you might be if you're on a space-based platform, a space-based platform. So this is calcium hydroxide. You can see it has a pretty unique absorption feature over here, around 2,400 nanometers. I can accentuate some of these features that you see in the plots here by doing continue remove. Blue acrylic paint, you can see this here as well. Pretty unique spectrum in here. Probably some plastic features. There's the blue, of course, that goes along with it. The left-hand side portion of the spectrum is the visible. So we can see, quote unquote, see with our own eyes this portion of the spectrum over here up to about 650 nanometers. And then anything beyond that is not visible to our own eyes. And then the spectrum that I'm going to focus on is actually urea. Urea is a fertilizer that can be used to obviously fertilize fields, fertilize backyards, blah, 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 whole bunch of things. Urea has a pretty unique spectrum as well, and you can see that spectrum as well. Urea can actually also be used nefariously as a homemade explosive or what we call an HME material if not used properly. So it can be turned into something called urea nitrate as a homemade explosive, but this is just the straight fertilizer material here that you see. So what I'm going to do is when you're using a spectrometer like something that Spectral Evolution has, you can see you get a really high resolution spectrum. So if you look down here in the lower left, you can see that out of this the spectra that gets provided, there's 2,151 spectral channels. We don't have that many channels with Orbital Sidekick. You probably could have put a spectrometer up there that has that many channels for a lot of money. That's not something that we have. We have 472. And then after the processing that I did that I showed you, I'm down to 168. So what I want to do is I want to resample this spectral library to this data cube that I showed you here. So I'm going to say spectral resampling, and I'm going to resample the spectral library that I showed you here. And I'm going to resample it to the input data file. That's memory number 5, and it's done. So I'm just going to close this guy, and I'm going to reload this. And you can see the urea spectrum is now resampled to the data cube, so 468 bands now. So I've now resampled the ground truth spectrum to the hyperspectral data cube that I just showed you. So it's now 168 spectral bands, this library. So now the library is ready to be processed against the data cube. So the algorithm that I like using is called the adaptive coherence estimator right here, or the ACE algorithm. So this is a form of effectively a match filter algorithm. And I am going to say I want to process this data cube using the ACE. Now it's asking me what's it. So I said I just gave it the cube that I'm going to go look for stuff in. So I want to take those spectral signatures and I want to compare them to every single one of the pixels in this data cube. And so now it's asking me, well, what signatures do you want to look for? Well, the signatures I want to look for are the one that I just resampled. So I'm actually just going to do the urea signature. So I'm only going to select that one. Y data multiplier. I've actually already multiplied this. I've already multiplied this library to match the Y scale that's in this cube. So I'm going to go ahead and hit OK. And I'm just going to, I'm going to select it. I'm going to plot it just to make sure I didn't mess anything up, which I did not. So you see the signature here. I'm going to go ahead and apply. I'm going to use a subspace background that allows me to make sure that some of the anomalies or some of the more extravagant signatures that are in the data cube don't get washed into the background statistic. I'm going to export that to the memory, and I'm going to hit OK. And it's going to go ahead and process this spectral signature against every single pixel that's in my data cube, looking for that particular spectral signature. And it is now completed. So now we have the ACE filter plane for urea. And so the ACE filter plane is on the left, is on the right-hand side, and my data cube's on the left-hand side. What I need to do is just threshold the ACE plane a little bit. Already I can see that my maximum ACE score is 0.71. For Orbital Sidekick data, that's pretty good. That's a pretty good ACE score. If I get anything above really 0.3, I might go look at it. for the spaceborne data. So now I'm just going to threshold this a little bit, and I'm going to hit apply. What I just did, I just got rid of about 98%, if not more, of the data. And I only want to look for what I call target scores or targets in the data. And I'm going to go ahead and maximize this. As you can see, it appears that I might have detected a few things in this data cube. These white pixels equate to detections, or what could be detections in the data cube. So I'm going to go ahead and link these displays together. And you can see here, if I flicker back and forth, this is where I'm getting detections from in our hyperspectral data cube. So I believe that I have gotten detections for urea down here, which is pretty good. So what I can do is I can just squeeze these bars together a little bit more so that I limit my detections to only really where the maximum scores or the maximum values are here. And what I can do is I'm going to load NVIDIA's ROI tool on top of and I'm going to select a few of these pixels, and I'm going to zoom in, and I'm just going to click on some of the ones that have really the highest detection scores. So that was what appeared to be an area on the bottom part of this cube, and then I'm going to go up to the top part of the cube as well, and I'm going to select some of these pixels as well. And so I've got 8 pixels selected now. I'm going to turn the ROI tool off, and I'm actually going to close the ROI tool out of the detection plane area, and I'm going to reload it just in the reflectance cube over here. And as you can see, if you look really closely, you can actually see my pixels that I selected, but now you're seeing them inside the reflectance cube. And I'm going to take this box down here, and you can see where these pixels are. What I'm going to do is I'm going to select this, and I'm just going to try to gather the statistics from those 8 pixels inside the reflectance cube. And you can see these are various min, mean, max, standard deviation, etc. The one I'm going to focus on is actually the average. So if I load a new window, and then I'm just going to take the mean, and I'm going to drag it to this new window over here. So now this is the reflectance spectrum, an average of those 8 pixels that we just selected from our reflectance cube. And if I go back to the spectral library, and I'm going to load that urea spectrum, and I'm going to turn that spectrum yellow for urea. I'm going to turn that yellow right here. I'm going to make the line just a little bit thicker, and I'm going to hit a block key, and I'm going to drag it over. So now what I'm doing is a direct comparison of the urea to the in-scene spectra. The in-scene spectra is white. I'm going to make that one, let's see, make that a little bit thicker in that line. And we're now doing a direct comparison. So I would not expect the in-scene signature to be necessarily to look exactly the same. Why? Because again, there's going to be a little bit of error from that atmospheric correction that we applied. But additionally, the urea that's out there at that particular place, it's not going to be a lab grade form of urea. It's been spilled out. There's now dust on top of it. It's been rained on. There's wind that's been blown on it. It's probably not pure. There's dirt mixing with it and stuff like this. But what I can do is I do a plot function and continue and remove. And when I do this continue and remove, you can actually see where I'm matching in certain portions of the spectrum here, definitely here. That's a pretty strong absorption here. And then maybe a little bit over here as well. But this is why I'm getting these detections for urea at this location. So you can see where, again, back in the data cube. And if I, let's see. So you can see there's probably urea at these locations here, and you can see where I've clearly detected urea at these locations, and that basically concludes the live demonstration. So here you've seen I've taken Spectral Evolution spectra, I compared it to our hyperspectral data cube. I've atmospherically corrected our hyperspectral data cube, and I've detected urea, from 500 kilometers away using signatures that that Mac provided me from Spectral Evolution. So what I can do is I can actually just go back to these charts. And this is, again, this is the data cube that I showed you earlier. And if I go forward, there's the detections. This is now a PowerPoint. You can see where the detections are at these two locations. There's actually 2 urea fertilizer plants in this cube, and that's what you see down there. I go forward. This is actually, these are photos that Mac provided of the material that was procured from Sigma Aldrich. So that's a pure urea material. Mac provided these signatures, and I ran them against this data cube here. And you can see where the urea fertilizer is located at these 2 locations. And again, graphical results. If I actually take those detections and I export them as shapefiles and I geo-register them and get them out, you would see where the urea is actually detected at this urea fertilizer plant. What's going on here? These are probably flatbed trucks here. They are coming around. They're loading the material onto the trucks here. And then the material is probably spilling out onto the ground at this location. And we're then detecting the spilled material out over this location. And that's what you're seeing here is the spilled material out over this location through here. So this is the other urea plant. These 2 places are about 8 kilometers or 5 miles apart. So this is Engro fertilizers. You can see these conveyor belts, this stuff, and also probably where they're loading and offloading some of the material here. But the conveyor is probably transporting material all throughout this facility. You might even see some on top of the roof here, and some spilled out on the ground over here. But again, good matches for urea at this location. So that was November 1st. There was another cube collected, 26 October. Same thing here. Oh, by the way, no EPA at this location, right? No EPA in Pakistan. So when they're loading this material onto the trucks and so on, some's probably blowing into this, what I believe is a habitable village over here. And then some fields are probably getting some free fertilizer, here, free fertilization, if you will, because the plant producing materials over here, and then it's just blowing in the wind over into this habitable village and then into these fields here. So that's what you're seeing here. Same thing here, 26 October detections for the material as well. Orbital Sidekick, we've done a few other things. This is ammonium nitrate. So same thing. I showed you how the processing is done, and then there's other things that we can detect as well, that not just urea that are out there. This is calcium ammonium nitrate at a place called Pak Arab. This is also in Pakistan where they produce ammonium nitrate. This is the same thing, different type of data collection called line scan. And you can see where we're actually getting detections for the ammonium nitrate at these locations here. This is El Nasser Company for Intermediate Chemicals, or NCIC, in Egypt. There's actually a big pile of sulfur out here as well. We detected that also. And you can see where the CAN 27 is getting detected here as well. It's really easy to go through these PowerPoint charts with you guys since I've showed the live demo already. I can just fly through some of these. This is Daragazi Khan, also a lot of stuff out in Pakistan. This, I think, is ammonium phosphate. I don't know that's for sure, but it's definitely an ammonium salt. This is UF4 to UF6 processing, nuclear-related processing at Pakistan. Really large whopper detection for an ammonium salt here. And you can see where it's detected. And again, a bunch of white materials out here on the ground. And if you want to know what those white materials are or which one is the ammonium salt, you got to have hyperspectral. That's what hyperspectral can tell you. Really good detection for an ammonium salt out here in this location. Sulfur, a lot of sulfur in this world. This is a petroleum plant at Bandar Abbas in Iran. And you can see where the sulfur is detected. So when they process petroleum, you actually separate sulfur from the crude oil. So you get these large piles of sulfur out here. You can see where I've detected it at Bandar Abbas in Iran. Really good match in the veneer portion of the spectrum for the sulfur. Port of Tocopilla in Chile. This is an incredible shot because we were able to detect both potassium nitrate and sodium nitrate in the same shot. So they actually mine for this stuff, is my understanding at at this location in Chile. This stuff is explosives. It can be used in fireworks or other explosive materials. And the absorption features for this stuff are in slightly different locations. This is why you need well-calibrated data in hyperspectral. This is also a really good reason why you need SWIR or shortwave infrared in hyperspectral, because without it, you're not going to see this stuff because you're all the way over here in the SWIR portion of the spectrum. I like using this chart to brag to our knowledge. Orbital Sidekick is the first to spectrally detect and demonstrate commercially from space the following materials: ammonium chloride, ammonium phosphate, calcium ammonium nitrate, potassium nitrate, sodium nitrate, sulfur, and urea. And there's probably a few other ones that are detected that aren't on this chart. But with that, that concludes the demo. I hope everyone enjoyed it. I hope everyone has a chance to actually utilize hyperspectral and spectral signatures from Spectral Evolution to compare them to Orbital Sidekick data or perhaps other data. And with that, I mean, I suppose we can take some questions or have some discussion. Over.